Okay.
How close are we to nuclear fusion? Will we know how to fuse atoms to produce electricity in a large scale before 2030? Is it a good idea to study nuclear physics to help with this field?
Again, those are questions of technology, and
Is
again,
it even possible to do nuclear fusion on Earth?
nuclear fusion we do on Earth. We do nuclear. We don't only do fission. We can do fusion. We merge atoms together. We have them run at high speeds and clash them together. But it's not the same fusion as the sun. That's my only comment there.
One is with pressure and
One is
with
the pressure, the
velocity.
other one's velocity, right? And that's the only
What's the
difference.
difference between doing it with velocity and doing it with pressure?
Well, again, all I can say is that I haven't been to the center of the sun yet, but
It's on your
if I
to-do
if I
list.
go there, I think what I'm going to find is a lot of pressure. It's like I'm going to, I'm squeezing in here. I think there's a lot of pressure, and it's done through pressure, and I'm not sure what the difference would be with velocity, except that I'm not sure the same thing. It's the same thing to press four balls together of whatever than to throw 'em, like let's say silly putty, something that would merge, right? Or mud. You make four mud balls, right? Is it the same thing to squeeze them together as to throw them at a certain point, at a central point, and have them merge or bounce out?
Well, that's the thing. It definitely isn't the same thing.
I would
You
think
can
it's
tell
not.
because when they do these certain things, isn't it that the two atoms essentially shatter?
Well, that's the point. The point is that they don't shatter the way they think it shatters. What they show always, and again, these are computer simulations, and we got to be very careful about that because they're not pictures, and people think they're pictures. Pictures of reality. They're not pictures of reality. They are simulations made with computers, and they're based on the particle hypothesis. So when they hit, you see all these little dots flying away from.
What are those dots?
Well, those dots are computer generated. They say, well, it crashed, and we have this big bang, this little bang, that created all this debris. But that's because they interpreted it under the particle hypothesis.
Well, what is the computer picking up?
Signals, and they turn those signals into particles. That's what's happening. And so they see it's like if they're measuring, the a little link of the rope, and they call that little link the torsion. For that split second, they call that a particle because it's it's localized, and they say, oh look, I was able to measure here and I felt something. That's a particle. No, it may not be a particle. What they may be doing is getting a cross section of the rope at that point. It gives them that little twirl. I'm not sure exactly how they do that, what equipment they use to detect that. But when they detect it, they automatically assign it as a particle and they say, oh, here we have a particle. And they have a way of doing this for countless particles. So every time there's a bang, a clash, remember they accelerate these things in opposite direction, the so-called particles. That's what they think they're doing. And then in the chamber where the clash is going to take place, they hit the two beams together and they say, okay, proton hit proton, or whatever, or atom hit atom, ion hit ion, whatever they've got in there. But then the equipment used to interpret that is already biased because they say any blip that we get out of that chamber is going to be a particle, and so they but it's like self-fulfilling prophecy.
But not really, isn't it that the machine detects, like you said, signals, and they interpret the signals incorrectly? The machine is just picking up signals. It's not doing anything. It's not saying these are muons that flew out. It's just saying signals. Something's happening here. Here's
and how are you going to put it in a computer to interpret it? How is the program that analyzes that? Because they don't take a picture of that. What they do is they run that through a computer. Now the program is going to interpret that. Well, they interpret that as particles. Wherever they found a blip, they put a particle. And so they paint this picture of particles, and that's what's misleading. Because they put a picture, like if you see the one from, the famous one from gluon and quark soup created from the collision of two gold atoms that they did at Brookhaven National Laboratories. Well, that's a famous picture because you see, supposedly, right, two gold atoms colliding in the center of the chamber, right? And they have all these particles coming out of that little bang, right? Well, where do they get the particles if that's not a picture? Well, they had to interpret that through some kind of program, some kind of computer or some analyzer of some kind, and they just, wherever they feel a blip, they put a particle. And that's why it's a self-fulfilling prophecy that you'll always get particles because the equipment used to measure is already programmed to understand every blip as a particle.
Couldn't they just program the machine to just call them blips instead of particles?
But then where would quantum be?